department at VJTI with 20 plus years of academic and research experience. He completed his PhD in Mechanical Engineering Department from IIT Bombay, where he specialized in microfabrication using reverse microEDM process. His research interests include micromachining, advanced machining, manufacturing management, manufacturing science, precision engineering, engineering metrology, and process engineering, along with other disciplines. He has published a significant research work through journals, conferences, and a book chapter, contributing extensively to precision and micromanufacturing domains. Dr. Mastood has guided 30 plus MTech dissertations and 50 plus BTech projects in collaboration with several industries such as Tata, Siemens, L&T, HPCL, Volkswagen, and Godrej. His achievements include receiving the DST Young Scientist Research Grant, multiple Best Paper Awards, and a DST Travel Grant for international presentations in the USA. He has held key administrative roles at VJTI, including head of mechanical and head of production engineering department, and has contributed significantly to NBA accreditation and TQ-based laboratory development. We are pleased to welcome Dr. Sachin Mastood to this one-week faculty development program, and also I am thankful to the course coordinator, Dr. Kiran Bhode, for giving me this opportunity to introduce my PhD supervisor. Thank you, sir. And over to Dr. Mastood now.
Okay, thank you. So I will begin my video for a moment and then switch it off. Professor Mega, slides are visible?
Yes, sir, it is visible, sir.
Okay, fine. So I'll switch off my video now. Fine. So, good evening all. Thanks Mega for nice introduction. Hope I will keep the space and complete the presentation or discussion on micromanufacturing in 1.5 hours. So basically in today's presentation, I will cover a few aspects of micromanufacturing and why micromanufacturing is important specifically to manufacture a bio-inspired surfaces. So content is initial. Since everybody is working in the domain of either mechanical or related field, and since the title of this ATAL program is closely relevant to the manufacturing, I believe that the majority of you have worked or know the micro manufacturing processes. So I will just brush off as simple as like it is undergraduate class for 50-20 minutes, and then based on that we'll build something on the micro manufacturing. Okay, so basically it would be covered in the three modules. Firstly, micro manufacturing, then bio-inspired design and manufacturing, and what kind of work I have done at IIT Bombay, specifically in micro manufacturing, how it can be used to develop the bio-inspired surfaces, that I will address at the later stage of the presentation. So start with so everybody knows how the mechanical processes works, mechanical machining processes work specifically. If you see the animation, it is adapted from one of the source. You can see that there is a direct contact between tool and the workpiece. Here, the workpiece is rotating. Tool is in direct contact with the workpiece. Chips are being generated. A continuous sort of chips are generated. And on the right corner, you can see the temperature profile on the tool, where temperature reached is in something 700 to 800 degrees centigrade. And so that's how there are many limitations of the conventional machining processes, including that tool must be harder than the workpiece, tool must be very strong compared to the workpiece. And there is a relationship, tool motion relationship between the tool motion related with the workpiece. So the geometry you can achieve in the conventional machining is limited. So based on that, now we are moving towards the micro manufacturing and 3D printing processes. Wherein we have more liberty over the geometry which we can achieve. Okay. And always remember that tool is in contact with the workpiece, and that fellow is under tremendous pressure, in the tremendous stress. You can see that is the machining force, and it is coming on this very limited area. So although force is high, contact area is small, so pressure is very very high, and tool has to bear this pressure. So always remember this, that tool must be very strong, correct, and it has to bear the pressure. Now, conventional it is possible, correct? You can make a thick section tool, but not in the micro manufacturing. So, these are the limitations of conventional machining processes. Which are the limitations? That there is a lot of heat, friction, vibrations are associated, because tool is in contact with the workpiece. Due to this friction, the heat and vibrations are generated in the workpiece. There is direct contact, so there is a tool wear is there, due to which there is the inaccuracy, poor surface finish. uh, all these are the limitations of the conventional machining processes. And most importantly, the motion between tool and the workpiece limits what kind of or which kind of shapes and sizes you realize with the conventional machining. Okay. Now moving ahead, we if you see the development of manufacturing process over the 100 years, last 100 years, we can easily see that each 25 years, I will again restate, each of 25 years our accuracy and precision is moving by 10 times. What it means, before 25 years, if you could have machined the part of, let us say, 10 micron accuracy, after 25 years it is shifted by 10 times, means earlier it was 10 micron, now we can machine the part of 1 micron accuracy. So each 25 years we are developing ourselves or enhancing the precision by almost 10 times. Not it is a 10 percentage or something, it is a 10 times. So considering that, we can now say that we can easily manufacture the meso parts as of now. Now there is a trend towards the micro manufactured part. Okay. Now why micro manufacturing? Why not the conventional processes enough? Why we want to move toward the miniaturization or micro manufacturing? So always remember that if there is one, let us say that there is one mechanical system, and the same function, same output, if you can get from the micro manufactured product or systems, why you will invest more material in the larger systems, correct? So if, for example, let us say that there is a one motor, and if the same output is given by the small motor, okay, advanced small motors, why you will invest in the large motor, where you will save more material, correct? More manufacturing sequences would be reduces, like that. If you want to reduce, if you can reduce, always try to reduce it. Second thing is that micro manufactured products are micro manufactured products are more, their response time is very high. That's how you see that in the, let us say that in the once there is a car accident is there, suddenly you will see that before you realize there is a accident and your head is collapsing on the or impacting on the steering, the airbags are already open. How? Because there is a micro system, and the response of the micro system is much higher than your senses, correct? That's why we always try to move towards the miniaturized parts or micro parts. Okay, because these devices are more faster, more sensitive also. But problem with the manufacturing of these parts is that what is called as a size effect. Now what is the size effects, which is specifically in the mechanical micromachining is, like on the right side you can see that there is a it is not the micromachining, you can say it is a nano machining. If you are removing only few layer of the machine, few atoms from the surface, the material provides lot of resistance. Okay, so the amount of energy required increases if the depth of cut reduces. Okay, that is what is called as the size effect. As the size of the depth of cut reduces, the amount of energy required to remove that layer is increases. And remember here that tool size is already reduced, amount of energy is increasing, so now it becomes more challenging, because tool size is reduced, cutting forces is increasing due to the size effect. Okay, so there is a first and important challenge in the micro manufacturing is to create the tools which can sustain this cutting forces. Okay, so that is the challenge, but yes, if you can overcome challenges, benefits are more. So now you will ask, what are the micro manufacturing processes? Correct. So as such, there are no separate classification of micro manufacturing processes. Whatever process we are using over the ages, if you scale down that process to such that it can remove the material in microns, that would be called as a micro manufacturing process. Okay, as such, there is no separate branch of micro manufacturing processes. Whatever we is practicing, only you have to scale down the process. What do I mean by scale down the process is like impact energy, or let us say that mechanical energy during the process is reduced. For example, let us say that you are carrying out turning of large part, very large part, big part on the factory floor. If you can reduce the depth of cut such that depth of cut is less than 999 micron, it would be called as a micro manufacturing. Okay, in micro manufacturing there is as such no separate processes, only the size of the feature you are machining on the part is less than 999 micron, that you called as a micro manufacturing or micro machining processes. So general classification is like there is a macro fabrication or machining, and there is a micro fabrication. Again, in micro fabrication there is a micro machining and micro nano finishing processes are there. In micro machining also you can see that the way we learn in our undergraduate studies also, like there is a mechanical based processes, there is a chemical based, there is a electrical based, correct? And so like that, in micro machining there is a chemical based process. For example, ECM is there, correct? So there is a ECM in conventionally, there is a micro ECM at the micron level. There is a laser conventionally, and there is micro laser, but laser size scale is so small that we conventionally also call that as a laser, not a micro laser. Okay, so EDM is there, there is a micro EDM, ECM, micro ECM, ultrasonic machining, micro ultrasonic machine. Okay, so like that, one thing is that you have to scale down the process so that it can remove, unit removal of material is very very small. Okay, so like that these micro manufacturing processes can be classified. Okay, so there is a conventional process, like there is a drilling, for example. So there is a micro drilling also, but only feature machined on the part should be lesser than 999 micron. So if feature is less than 999 micron, then your tool should also be at a micron level. For example, drill of, let us say that you want to drill a hole of 100 micron, for example. So in that case, we need a drill of 100 micron also. If you relate it, our hair size is close to the 80 micron. In laboratories, we can drill a hole of less than 80 micron also. So it means that you can drill a hole on our hair also, correct? There are drills of less than 40 microns, 50 microns are available. So you can literally drill a hole in our hair, because hair is 80 micron, our drill size is 50 micron. But now you can realize drill is there. Conventional drill, even if you fall on the floor, it will break. So now here is a micro drill, which is size of less than a hair size. Drill, you know that in the drill there are the all fluids are there, so you have to make that fluid at the micron level also. So that is foremost challenge in creating the tool. Okay, so all manufacturing processes scale down, these are the micro manufacturing processes. But yes, constraint is it should machine the feature or create the part of less than 999 micron. Okay, less than a mm. Okay, so that is a constraint, and based on that the micro manufacturing processes are defined. So out of these micro manufacturing processes, there are the mechanical processes like ultrasonic abrasive jet, water abrasive jet, beam based processes like energy based process, basically EDM, ECM, laser beam, ion beam, plasma beam. All these are the processes, okay, wherein I am more concentrating on the beam based processes and the EDM, which I have highlighted here on this slide. Okay, we'll come to this point. So as I mentioned, four most important challenge in the micro manufacturing is the usage of the tools and getting those tools available at your facility. So as of now, we are lucky that these tools are easily available in India. 10 years back, we have to import those drills from the Singapore, and the size of the drill is so small. Size of these milling cutter drills is so small and so expensive that half of the drills, while in transit only, they will be break. Okay, because they are so small. Okay, they are so small. Someone has unmuted. Can he or she mute?
Yeah, I've taken care. Yeah, Dr. Sachin, you proceed.
Okay, so that is the first challenge. But the image shown here is close to the 40 micron, correct? Close to the bottom drill is of it is a milling cutter actually. It's a 40 micron, and you can see that the flutes are machined on the 40 micron. 40 micron is what? Is a half of a hair size. On the half of the hair size, flutes are machined, and now you expect that this fellow will cut the metal. That is more challenging again. Another challenge in the building the micro machines is normally how we calculate the RPM required on the machine. For example, if you go to the workshop, you are carrying out turning operation. Now, how will you evaluate at what RPM the workpiece should be rotated? You will evaluate that based on the simple formula, V is equal to pi dn by 1000. Now, V is a cutting velocity. For the carbide and the mild steel, let us that cutting velocity is 100 meter per second. Based on that, you will evaluate the RPM. Now, conventionally, let us say that for turning the 10 mm workpiece, the RPM would be around 3000 RPM. But if you reduce the drill size by 100, your RPM will obviously increase by 100, and it will become sometimes 2.5 lakhs RPM, which is not technologically feasible. It means that you will rotate this drill at 2.5 lakhs RPM, correct? Which is, as of now, is not possible. People have reached to around 1.5 lakhs RPM, but again, these are advanced machines. They are using the super balanced spindles. They are using aerostatic bearings instead of the normal bearings. Okay, and then they will rotate this sort of tools, and then you expect that it will drill or carry out the milling operation. These are the challenges in the mechanical micro manufacturing. Irrespective of those challenges, there is a good thing that in India we are now manufacturing the drills or the milling cutters. So there is a company, there is one company in the Himachal Pradesh. It is Axis Micro Manufacturing. This Axis Micro Manufacturing has got they have developed the capability to micro manufacture or to manufacture this drill in our own country, and that's how this cost of these drills are now reduced. Remember, the drill size of around 80 micron can be easily manufactured nowadays in the India, which otherwise we have to import from the Singapore in 10 years back. So so general manufacturing of this tool is always first of it's a design. Okay, correct? You have to design the flutes, shanks, and then there are the 5-axis grinding machines are there, which will cut those drills and the milling cutters. You can see the size of the drilling and milling cutters. So online metrology has to be followed so that you can measure the diameter of the drills and those. So these are the drills, non-contact measurements you have to do. All these are possible in India, and we are now able to manufacture the micro drills and milling cutters. Okay, so this is a good company. Axis Tools are there, and their tools is almost reliable. Okay, their tools are almost reliable nowadays. And earlier there's like these tools, uh, they half of they used to be failed in transit only, in transportation only. But now reliability is good, and we can use this micro drilling or milling tools in our setups. Only thing is that normally you cannot mount this micro drills on the, let us say, that drill machine available in the workshop, because you have to rotate these milling cutters or the drills at very very high rpm, and at high rpm it has to be balanced, correct? Otherwise, see, the diameter is only 50 micron. Even if you slightly touch the workpiece on the cylindrical side, on periphery, it will break. Okay, so these are the challenges. So irrespective of those challenges, we can now able to fabricate the parts at the micron level. Now, by definition, the part size may be large parts, but as I have defined earlier also, that the feature size you are machining is less than 999 micron, that we called as a micro manufacturing. Okay, so where you will use the micro manufacturing? Basically, micro manufacturing is used to produce micro parts. Now you can manufacture different micro parts, assemble that in the micro products, okay, and expect that it will function. Take an example of advanced cars only. In advanced cars, almost more than 500 sensors are there, which need manufacturing at the micron level. Be it the sensor, be it with the uh, uh, a sensor which operates, let us say, that tire pressure, or which help us in the monitoring the ADAS system. There are multiple sensors are there. These are integrated in the systems, but manufacturing of these sensors, you require a micro manufacturing capability. Okay, so there are numerous examples of this wherein micro manufacturing is required. So presently, where we are, okay, what is capability? Our capability in micro manufacturing. Our capability in micro manufacturing is reached to almost a saturation level. Okay, how? You can see here a fourth image on the which is a face of human, wherein that size of the face is 1 mm. Okay, and by which process it is made? It is made by the micro milling process. Now you can imagine that the feature size is 1 mm. How it could have been made by the micro milling process? Now, to make these features, the milling cutter has to be very very small, very very sharp. Okay, so you have learned in the your machine design courses that if the diameter of the shaft is reduced by, let us say, that half, its strength is reduced not by the half, but by, let us say, that one by one, it will remain by 1/4 only. It is not a, a linear relationship. It is a it is a square relationship. Okay, so if size of the tool is reduced, its strength is tremendously diminishes, correct? So size is reduced, and you expect that that fellow will cut the metal and realize such a beautiful features on the metal. Okay, such is the challenging, but yes, micro manufacturing processes has reached the competency level, and you can easily manufacture such a features in your own laboratories. Okay, be it with the manufacturing of such a face type of features, or develop a micrometer close to a match size, half of the match size, be it with the development of the uh, advanced, gearing systems which is used in the smaller micro parts, be it with the development of the micro gears. It is made by the laser sintering process, cutting something on the hair of 70 micron, something 25 micron characters are written there, or development of this pagoda system, pagoda features at NTU Taiwan. It is in NTU University, it is made. So presently we have a lot of capability to manufacture these parts, but we have not realizing the applications, because design engineers don't know that such a advanced manufacturing facilities capabilities are there. So they are not using this design in their design features. Okay, but ultimately we are had now reached to the level where we can easily manufacture the parts of 10 micron. Below 10 micron it would be difficult to go, because now you have to reach to the crystal level of the material, which is around 3-4 micron. Correct. So only there would be few layers of the crystals would be material would be remain there, which is difficult. Okay, so now this covers the micro manufacturing. We have reached wherein we can manufacture very smart parts, like be it with the crown on the ant, or the this ant holding the gear. Although in the same that was it was transparent, but it is actual image. Okay, just to notify, it is colored with the red, but otherwise it's the actual image. Okay, such a features you can machine. Again, as I to summarize, like micro manufacturing, it uses the same principles of uh, same principles which are there in the conventional machining, be it with the mechanical use of the mechanical force, be with the melting and vaporization like a laser, EDM, EBM process, or ablation like in the excimer laser or femtosecond lasers, or be with this die casting or injection molding processes. So there is a casting, there is a micro casting, there is welding, micro welding, rolling, micro welding. Correct. So all these processes are dissolution, which is used in the ECM process or photochemical machining process. Similar principles is also used in the micro machining process. Okay, but only thing is that it is difficult because metals tools are creating the challenges, and importantly there is always the presence of the size effect. Okay, so different types of energies are used in the manufacturing, like mechanical, chemical, electrochemical, or be it with the corrosion with the photochemical. These are the methods and the processes with which micro manufacturing is working. I will not spend more time because it is almost similar to the classification of our unconventional machining processes. Correct. So now moving ahead, uh, let us say that we wish to do the micro manufacturing process, but as I mentioned, you require a dedicated machining facility. So as of now also, I have worked this in the almost 7-8 years back at the IIT, but still IIT Bombay has a good micro machining facility. There is a micro machining cell available in the IIT Bombay, wherein they have different machines. Out of them, there is one machining center. There is a difference between machine and machining center. Correct. Machine is dedicated. Machining center is with change in the spindle and tools, you can carry out the different operations on the single setup. Like for example, you can same frame can be used for the microedium. Same setup can be used for the micro ECM also. Okay, so this is a machining center, and as well as there is a micro drilling, micro milling, micro turning you can carry out on the this same facility. That's why it is a micro machining center. Now this micro machining center, previously it was developed by the National University of Singapore. Professor Rahman is there who developed this center. IIT Bombay has imported this machine in the Singapore. That this was their first machine developed by Professor Rahman. Now there is an advanced machine. There is 100. This is 100. DTI 100 is the machine, but now there is a 110 version is came, and IIT Bombay has recently procured that machine, and it is active in the micro machining cell. Now, good thing is that this is the Micro Tools. Micro Tools is the manufacturer of micro machining center. Now, this micro machining center, as I mentioned, with the different change in the tools or spindle heads, you can carry out micro drilling, milling, uh, or micro EDM, micro ECM. All these operations can be done in the single setup. Okay, it is advanced machine basically. Why advanced? Because it is a vibration proof machine. because at the micron level, once you are doing the machining at micron level, even slightest of vibrations will break the tool. Okay, that you have to control. So just we'll go through the video of this micro tools. It is a machine there, okay, in the IIT Bombay. It's 100 DT 110 machine is there, okay, which is basically the world's first micro machining center. This is micro turning being done, okay, micro EDM, okay, wire EDM is there, okay, this is wire EDM, micro wire EDM. So on other thing is that this machine has a capability to measure the dimensions in situ. Means what? You can measure the dimensions when the part is there on the machine itself, because you cannot remove the part and machine it and then again mount it and carry out the processing. You have to measure the part in the when once it is being machined in the on the machine itself, correct? So this is a micro milling, okay, like that. Micro milling, micro drilling, all these processes can be done in the setup only, in the given setup. We'll just move, push it. So what kind of part it can machine? There is one good example you can see. This is the mechanical machining, okay. What they have done, they have created some this thin wall structure, and the width of this thin wall is close to the 70 micron, and it is made by the micro milling process. Okay, all this material is removed between the thin walls, and you can see the aspect ratio of thin walls is also good. Okay, so these features you can machine on the micro machining center at IIT Bombay. Okay, so there are at the end there are good examples also. What kind of good examples? In the sense, see here, this is a micro shaft. You can see it is micro shaft. It is done by the turning. Now you can you imagine, like, this is a 1/8 of our hair size. Diameter is 100. Diameter is only close to the 10 micron, and see, it is made by the turning process. So much is the precision and accuracy of that machine. Okay, there are, and via this system you have to measure the dimensions. It is an online camera is there. With that you can measure the dimensions. It's a micro turning. Okay, this is a hybrid process where two setups are there. You can carry out micro turning and then micro EDM, because you cannot remove the some of the parts. So earlier turning is done. Now they will use this for the micro drilling operation, micro EDM operations. You can see the sparks, correct? So it's a EDM process. Okay, so like that, with this process you can machine numerous parts with the micro hole of less than 6 micron. You can imagine, less than 6 micron micro hole is made by the micro EDM process on the process. Okay, so we have this facility now. At the earlier start of our research, we thought we have the facility, but can we use this facility to create some bio inspired surfaces? So now we move towards the which kind of bio inspired surfaces are there, and can we manufacture some of the bio inspired surfaces in our own labs? Okay, so bio inspired surfaces recent only gain more traction and more importance, in the sense that many of the applications are evolved by inspiring the design from the which is already there in the nature. Okay, why nature? Because nature has developed itself since millions of years. So some of the systems are there which are very complex, but nature has beautifully developed that, which we can adapt in our systems. So there is separate branch of this, and it is called as a biomimetics, which means that mimicking the biology or the nature, and develop the different applications, be it with the mechanical, not limited to the mechanical, but other applications as well. So I will go this at the little bit faster through these slides, just to synthesize that what kind of applications can be evolved, and can we use this application in our own laboratories. So bio-inspired surfaces shows different properties. Some of the surfaces, they are very less friction is there, whereas some another surface very high friction is there. Some surfaces is which has property of hydrophobic in nature, some properties which are hydrophilic in nature. So nature has beautifully developed this, and it has developed this by playing at the micron level. So if you see the surfaces under the microscope, you will see that each of the surfaces has different morphology. Okay, on each of the surfaces, different macro scale or nanoscale features are there. Okay, which helps us to obtain different properties. Which are those properties of interest for us? Can we develop, let us say, that super hydrophobic surface, self cleaning surface? Can we reduce the drag in let us say that ship is moving in the sea? Can we reduce the drag so that we can have more economical uh, or mileage of the ships would be increased, like that. Similarly, it can be used in the energy conversion, either conversion or be it with the other properties like aerodynamic lift. Some of the birds, they have beautiful aerodynamic, they can lift, so that in the slightest of the their wings, flip of the wings, they can accelerate. Similarly, there is anti-reflection properties, thermal insulation, like polar bear is there. Many of the HVAC systems are now inspired by the polar bear material, on the wool of the polar bear. So these are inspired. Okay, so these are some of the properties which we are inspiring from the nature, and which uh, attracted most is a hydrophobicity, or which is also called as a lotus effect, which I also explored in the laboratories, which I will explain further how we have explored that. Okay, similarly, this bio-inspired surface has very high industrial significance. Like people are trying to develop their climbing robots. Nowadays, the Olympic swimmers, they are using the whole body swimsuits instead of the earlier, the limited suits. Similarly, from polar bear, we have inspired like artificial furs, and the textile industries are trying to explore those artificial furs inspired from the polar bear. Okay, so nature is teaching lot of things to us. We need to inspire. We can inspire from either bacteria, plants, insects, spiders, a lot of aquatic animals. For example, aquatic animals, they have low, specifically they have the low hydrodynamic drag, so that aquatic animals can accelerate even if there is a resistance of the water. Still, they can accelerate very easily. From birds, we can learn like aerodynamic lift, light coloration, like our national bird is a peacock, correct? It is very colorful, but in reality, the feathers of the peacock has only color, which is no color at all on the feather of the peacock. It different it reflects light in the different direction. From that, we realize that the peacock has a, because wings have different colors. Actually, there is no color ligments in the peacock feathers. Similarly, we can learn from the camouflage from the birds, insulation properties from the birds. Like that, there are many properties we are trying to explore and learn from the nature. But more importantly, the super hydrophobic surfaces, which I inspired from the nature, and we try to develop super hydrophobicity in the laboratories. Okay, why super hydrophobicity? Because as I mentioned, if you see any surface under the microscope, you will realize that different surface has different geometries. For example, let us say that whale is there, or shark is there, not the whale, shark is there, which has the textured surfaces. Okay, and that textured surface is coated with the natural oil, so that whale is an animal which can accelerate at the highest velocity in the which is large aquatic animal. compared to any of the large aquatic animal, whale has the highest acceleration. This is mainly due to the this texture surfaces on it. Okay, so like that, we need to learn much more from this and try to explore the properties, be it with the large aquatic animals or the small bacteria. For example, the flagella bacteria rotate at 10,000 rpm. Okay, and it inject it basically, there is a nano motor is there, like this, there is a nano motor is there which works on the protein. Basically, a proton flow is there, and you can imagine like the bearing tolerances are close to 20 nanometers. Okay, and sometimes the clearances are as small as 1 nanometer. So such type of features are there, and now people are trying to explore this in their designs. Okay, from plants we can learn a lot. Like for example, the outermost layer of the plant is hydrophobic, which again, as I mentioned, I need to explore that. This is what I inspire, that this is a lotus leaf, uh, wherein even if it is in the water never sticks on the this lotus leaf. If you put the some drops of the water on the lotus leaf, it will never spray down the lotus leaf. Rather, it will form like a drop. It will stick there itself as a drop. And then question is why. The question is why, like the answer is, on the lotus leaf there are the micro features are there, and on micro features there are the nano features. Okay, so now we decided, can we manufacture mechanically machine the lotus leaf surface in the laboratories? That is our challenge. Okay, similarly, there are many of the applications which we can explore, like for example, chemical defense of the plants, which is mainly due to the nicotine. Some sort of nicotine is there, which is also there in tobacco. Due to small amount of this nicotine, the other insects never attract towards these plants. Okay, similar problem is faced by our let us say that defense personnel, which who works in the forest at the border. They are not suffered by the enemies, but they are more suffered by the mosquitoes and these insects. So now people are trying to use this in the development of some waste or something, where insects or these mosquitoes would not attract towards them. Okay, so like that, velcro effect is very popular. Pond skater is there, which can hold it can stay on the water. Not only stay on the water, but it can carries the weight of 15 times its own weight, and after that only it will sink. Till that time it will stay on the water. Okay, so if human weight is 100, you can imagine that you are holding in the 1.5 tons of the weight, and still you are standing on the water. Like that, the pond skater is there. So pond skater, it shows that nature, mainly because there are these antlers, are these features are there on their legs, which spreads the water basically. Okay, so there are many applications. I will just go through this. Mosquito eyes, which is anti-reflecting nature. This is a water harvesting beetle is there. Specifically in deserts there is no water, correct, but there is lot of moisture in the deserts. And most of the deserts are very close to the seas. So over the seas there is a air is flowing, and in that air the lot of moisture is there. But on the surface there is no, on the ground there is no water, correct. So how this beetle, it condense that water. How it condense that water? It keeps his uh, feet against the flowing air, and it has micro channels on his body. And once the that air is flowing through these micro channels, due to large surface area, this the moisture in the air, they condense. And due to this, the water droplets get accumulated on the surface. And one good thing is that there is a one micro channel, and due to this capillary action, this micro channel is get filled, and automatically this drop comes to the mouth of this beetle. So like that, these desert animals, they are surviving without water by condensing the water. So even people are now trying to, can we condense the water which is there in the air, Can we make a device, at least if it is, even if 10-15 liters of water can be condensed, it will give the enough water for the a small family. Like that, people are trying to explore the things, be it with the climbing frog. Our tires are now inspired from the frog, so that it can stick on the sliding surface also. Walking robots. So like that, there are multiple applications are there. I will just brush up those applications. Some of the specifically the birds are there. They are oliphobic. Oliphobic means what? That lot of oil tankers are there, and if some oil is leaked from the oil tankers in the sea, the aquatic animal suffers a lot. But it is found that some of the birds are there, even if they can dive in the this olive oil water filled with the oil, and still that oil would not stick on their feather. Okay, so oil is sticking on some of the birds, but it is not sticking on the other birds. So people have studied where this, why not on the other birds, and based on that, now they are trying to develop the surface inside the water, uh, that not water tank, the oil tanks which are carrying the oils, so that at the end, once a tank is decontaminating, all the oils can be removed from the on the surface. Otherwise, what happens, some of the oil stick there itself on the surface, and you have to clean the vessels before you are putting some different chemical there. Okay, so complete decontamination been done. Similarly, the flippers of the whales, nowadays wind turbines are inspired from the whale flippers, and it is found that they work even if the air velocity is lesser. They have become more efficient, because the angle of attack has increased. Okay, similarly the birds, there is a, as I mentioned, the peacock, there is no color pigments, but the reflection in different direction creates this camouflage actually. Okay, similarly the robots, they are inspired from the elephant trunk, which has a more degrees of freedom. Correct. Bat inspired robots, the famous problem of the bullet train. Once the bullet train leaves the tunnel, it was making lot of shouts, a sudden blast, sort of sound was coming. So that problem was resolved by making this close to the peak of the kingfisher. Okay, and that problem solved. And also the overall, it becomes, trains becomes 20% more fuel efficient. Good example. Deer antlers, it has driest surface, but it is hard surface. Okay, that anything which is very dry is brittle, but this is a brittle means it is very less hard. But this is only the surface which is very dry, but it is also very stiff and hard. So a lot of things are there which we need to learn from the nature. Okay, bio inspired needles are coming, so these needles will vibrate while injecting in the human body, so that you will not feel the pain of needling. There is a one the shopping center is there in Nairobi, which is inspired from this termite mound, and it is consuming about 10% of energy which is normally consumed by the this type of buildings. Okay, so there are multiple applications. The most thing I inspired is the lotus leaf. Okay, now as I mentioned, we want to create a surface in the laboratory which is inspired by the nature. We have taken the inspiration from the nature, and now our task is to make the hydrophobic surface in the laboratories. But hydrophobic surface like lotus means what? Actually, if you see the lotus leaf under microscope, you will see that there is a bump of around few microns. Okay, like a semispherical features are there, and on the semispherical there are the rods. So we took that challenge, and we thought, can we develop the process where we can manufacture high aspect rods as one problem, and can we make a textured surface like a lotus leaf? Lotus leaf has a textured surface. Texture means what? Same pattern is repeated thousands of times. So Our first task was to make, can we make these high aspect ratio features on the laboratories, obviously with the micro machining, or can we create the thousands of these features on the surface, which we call that as a textured surface. Okay, so these two problems we have taken. Why two problems? Because with the first problem you can solve the these are high aspect ratio features used. Let us say that there is a electrode of the microbacteries. So instead of single electrodes can be a multiple electrodes. Okay, but how to manufacture these electrodes, it's a challenging. So we took that as a challenge. Let us manufacture that. So first aspect is manufacturing these few features, but aspect ratio is very large. Aspect ratio is what? The length to diameter ratio is large. So these electrodes are used in the micropins, heat exchangers, micro batteries. Also, these are used to capture our brain signals in some biomedical devices. So we require that. So existing processes are there. Like for example, you can use the milling cutter. For example, like here, you can use the milling cutter, make a cut in this way, horizontal cut, vertical cut. You can make post like this, but you know how much challenging is in the milling cutter, because I started with the challenges in micro machining, because this milling cutter is so small, you will cut only one post and it will fail. Other way, you can make a micro wire idiom, make a cut in one direction, cut in normal other 90-degree directions. You can make a features, yes, but different features you cannot machine with the this process. So with these challenges, we said, can we develop the process which is our own process, developed at the IIT Bombay. And uh, and I was working there for my PhD work with Professor Suhas Joshi and Professor Ramesh Singh. Under their guidance, we have developed this process, which we called as a reverse microidiom process. Reverse microidiom process. Why reverse microidiom process? Here, the image A shows at the top shows the EDM process, microidiom process. Microidiom process, you know that is a EDM process, basically scaled down to the micron level, so that you can machine the micro parts. In EDM process, if you recall, we are using the cylindrical or not the cylindrical always. It may be rectangular or other rods or features to make the cavities in the surface. Correct. So initially we take a rods, we make a cavities in the EDM or conventional EDM as well. So you will make a dies, you will make a cavities, pockets with the process in the EDM or micro EDM process. But what we wish is manufacturing of these rods, correct? So now how will you make these rods in the reverse EDM process? So initially what we have taken, with the rods you can machine the cavities. So we have reversed this. Initially we have taken the cavities and then made the rods. So the difference between microEDM and reverse microEDM is tool electrode. See the geometry of the tool electrode. In earlier case, it was the cylindrical rods. So you will make a cavities. Here we have used the uh, here we have used the here we have used the cavities and make the rods like this. So initially we can make the rod these cavities, required cavities, by the laser process or micro drilling process. Let us imagine that you have made this 100 three holes, 100 micron 100 micron three holes on the plate. Workpiece is there. You have aligned the workpiece on the cavities. So these three holes are there. So once you try to do the micro EDM, what will happen? Spark will generate whenever there is a metal to metal interface, correct? And you will make these three rods. So you keep on continuing. If you keep on machining, what will happen? The material would be eroded from this area, correct? All this area, because here there is a metal to metal contact is there. Whenever there is a hole, you will get the rod out of that hole. So the geometry of this cross sectional of this rod would be equal to the cross section of the hole. Okay, so you can now play with the cross section of the hole and get the rods of different cross section. put the multiple holes, you will get the multiple rods. So like that, you can see here we have used this as a electrode where I have made the 100 by 100. There are 100 holes initially on the plate, and with this 100 holes, I have made the 100 rods on the surface. Okay, so this process uh, we were second actually. Prior to us, there was a Kim et al. Who has developed this process. We have explored this in our laboratories. So from cavities, we start machining the rods. That's why it is called as a reverse microEDM process. Okay, the same Kim et al. He has developed this process. Okay, so now it is very clear that base, if you use the from the holes, you can make a rods in the on the metal. Now it is very challenging to make it on the metals. On polymers and other materials, soft materials, it's easy. It's easy to make multiple cavities with the lasers, but there were no process which can give the multiple rods of different cross sections, and basically you can play with the cross section and the aspect ratio also. But again, the challenges, this was the end of the efforts of 4 years. Okay, it was not that much easy at the start. Initially we started with very few rods of only we try to machine only 2 rods only. Okay, and these rods of very easy to material. Now in the EDM, what is easy to material and what is easy to erode and what is difficult to erode material? Let us say easy to erode material is brass. Why brass? Melting point is only 700 degrees centigrade. Difficult to erode material is titanium, where melting point is about 3000 degrees centigrade. Correct? So you cannot machine the titanium with easily with the microEDM. Okay, so initially we started the machining with the very softer materials like a brass. Initially we have taken only 2 rods. Okay, if you recall again, our objective are two. One is to make a rods of high aspect ratio, and second is to make the bio-inspired surface which is super hydrophobic. Okay, so initially on the first year of research we could able to machine only few rods of here, a rod of 400. This is a 400 and this is a 200 rod, 200 diameter rod. 400 is a square rod. So what I have taken the plate like this, where I have made the one square hole of 400 micron, and another is a hole of 200 micron, and based on this 400 square and 200 circular, I have made these 2 rods. Then we quantified like what are the important processing parameters. You know that all this basically initially we played with the processing parameters. But what are the results? Results were like it was 100 and 200. Expected was 280 micron. Expected was 80 micron, but you can see somewhere it is 50 micron, somewhere it is 231 micron. Expected was 80 micron, correct? So you can see lot of taper is there on the surface. Why there is a lot of taper? Because during machining there is a sparking, and due to the sparking the hole was also elongating. So with as the rods are getting machined, the holes will also get elongated, and that's why there is a taper on the surface. But somehow initially, with a lot of efforts, we could able to manufacture only 2 rods, that on softer material. Okay, we quantified, we played with the process. Okay, and here I would just suggest that always try to make the problems very primitive at the stage. We take very brass material. Our objective was to make thousands of the rods, but we started with manufacturing only 2 rods, that on softer material. Once we were more confident on the process, then we quantified what were the percentage error in the diameter. You can see we expect such a huge percentage error in the diameter is there. 80 micron we expect, but the errors are 60 percentage. Correct? 60% of 80 micron is around So we expect a diameter of 80 micron, but we are getting the diameter of 120 micron, like that. So a lot of defects were there, correct? Although we expect single rod, but you can see the diameter here it is 51, here it is 231. So huge difference. But yes, somehow we machined it, we get the knowledge, we quantified the surface finish on that, we understood where the process is stabilized. We could be able to produce this paper in 2009, much earlier, in Journal of Engineering Manufacture Part B, uh, about just the introduction of reverse microdium to the micro manufacturing, microdium specifically, researchers. What is this reverse EDM? We quantified that. After we got the significance, let us now say that make it more challenging now. Instead of machining these rods on the brass, let us make that these rods on the tungsten carbide. Now tungsten carbide compared to the brass, so anode material, workpiece material is a tungsten carbide. So tungsten carbide is again it's a material of high melting point, again close to the titanium, about 3200 is close to the melting point. So again it was poses lot of challenges to us. Earlier case we were machining the brass with the copper electrode. Here also we tried machining tungsten carbide with the copper electrode, but we failed miserably. Second challenge is like where we are using the cathode, that thickness of foil cannot be higher, because we have to ultimately make a drill initially and use this drill to make the holes, make the rods. So we cannot make a thick holes, thick we cannot take the thick sheets of the metal. We need to take foils and then initial holes on the foil and use that as a tool to machine the workpiece. So we failed miserably. We explored many materials, but ultimately we could able to get it. We could get the success only when we use the tungsten copper as the electrode material instead of the copper. So we cut the tungsten carbide with the tungsten copper. Again, we quantified, and it was better, like compared to the earlier case. Here diameter is reduced, but the dimensions achieved on the rods is very, very good. And we could able to machine the rods of around 70 micron and see the accuracy of the rods. These are the diameter 70.3, here 77.4. These are the diameters of the rod. We could perfectly make these rods in the workshops. But again it was very primitive. We don't expect 2 rods, 3 rods. We make thousands of rods, so that it is a biomimetic inspired surface, lotus leaf kind of surface again. But that was also significant results we got, and we could be able to produce that in the publish that in the International Journal of Manufacturing Technology and Management. We could publish that results. After that we also tried to make it on the curved surfaces. How small we can go? We can go to the around 24 micron also. All these features are machined at the IIT Bombay only. Okay. So but again ultimate aim was thousands of rods. Okay. But before going to the thousands of rods, we were interested in comparing the process, like reverse EDM and micro EDM. What is the comparison between them? And specifically those who knows the EDM, the best way to do is to capture the voltage and current signals and then measure it. So we quantified the voltage current signals using this sort of oscilloscope and the current probe, and we compared the reverse EDM and micro EDM. We found that yes, there is a due to the inherent nature of material removed, because in reverse EDM you are machining the rod, and in the micro EDM you are machining the hole. So based on that, the voltage current signals we are getting is different in the different shapes. We quantified that, and quantified those results, and we could able to produce that in the one of the ASME conference in the US. We could publish these results. But ultimately what our aim was lotus leaf, as I mentioned. Again, lotus leaf, it's not easy. It has thousands of micro rods. On the lotus leaf you can see these spherical rods are there, If you see this lotus leaf under microscope, there are the rods, and on this rod there are the, like, these nano rods are there, which we want to create, and there are thousands of rods. If you see the earlier our two papers, we could be able to produce only two rods, few rods, but ultimately thousands of rods. And that too now we are making more challenging. That initially we did with on the brass, second time we did on the tungsten carbide. Let us let us make it on the toughest material to erode, which is the titanium alloy, Ti6Al4 vanadium, titanium, 6th grade of titanium, which is aerospace material. It's a biomedical material. We thought, let us make the titanium, this material, super hydrophobic. But how to make it? It was very challenging. Initially, we tried to use any of the tool material, any of these things, but we failed miserably. We were not able to machine single rod. Forget about making the thousands of rods. Then we thought, let us enhance the process. How will you enhance the process? Those knows the EDM process. During the sparking, everything is in the dielectric, correct? In the EDM process, we are using the dielectric. Whenever there is a spark, this material gets removed and it is immediately solidified, because around that there is a dielectric flow is there. We will make a dielectric flow through these nozzles, and if that material remains there itself, it creates the short circuits. Okay, and precisely that was happening while machining the titanium. Lot of short circuiting were there. So we thought, let us remove this short circuiting. So what we have developed, what is called as the ultrasonically assisted reverse microEDM. I will repeat, ultrasonically assisted reverse microEDM. What is ultrasonically assisted reverse microEDM? Is this tank where reverse microEDM is happening, we have mounted that on the ultrasonic actuator. Okay, this is an ultrasonic transducer, and this ultrasonic transducer is vibrating this tank vertically. Okay, so this is vibrating the tank vertically, so that the gap between this is a cathode and this is anode. This gap is continuously changing because this plate is vibrating, correct? This plate is vibrating ultrasonically. So once we have put that, the problem was immediately solved. Okay, so now rod is being machined and the plate is vibrating at ultrasonic frequencies. So what happens, the gap between the plate and the cathode and the anode continuously changing, and due to that we could able to machine that. And remember that without ultrasonic we are not able to machine single rod, but with ultrasonic of low frequencies of, let us say that 6 kilohertz and 3 kilohertz and 6 kilohertz, an amplitude of only 0.5 C, so how small amplitude is, but with that amplitude only the problem was solved. Because as of now also in the microEDM, the gap is around tens of microns, so even 2 micron of amplitude is enough. It's around 1-2% of that is enough. So we could able, what I have taken now, I have taken the thin copper foil. Okay, thin copper foil. There I have made thousands of holes with the laser ablation. With the laser, I have made these thousands of holes. These thousands of holes, I have this. It is so this on this plate thousands of holes are there. So I have taken the plain workpiece now, aligned that, and then I have made thousands of rods, micro rods on the surface. Why thousands of rods? Because on the lotus leaf also there are thousands of rods, and due to this only it is exhibiting the super hydrophobicity. So use of this ultrasonic, what it leads to make these rods. So this only small portion is extended here. You can see this is extended here. Again, this small portion extended here, small portion, same image extended here. So you can see close to this rod is up close to 40 micron. On lotus leaf, it is close to 5 to 10 microns. But yes, it is very close to the hydrophobic lotus leaf. Below it is very difficult because this hole cannot be machined lesser than 40 micron. That is limitations of the lasers also. So none of the process you can machine that. There is always entry electrode gap. So there is a limitation on this. So smallest we can go is the 40 micron. So now you can see this is the titanium surface of around 4 micron. This diameter is 4 micron. Remember, initially we were not able to machine even single rod, this rod. But here we have made thousands of rods on the surface. And why thousands of rod? Because we know that this is a lotus leaf geometry inspired from the lotus leaf. So without vibrations, there was long short circuiting, but with vibration assisted, there is no short circuiting. So this is with the without ultrasonic vibrations, no shorts. There were a lot of short circuiting, and in EDM, short circuiting is material is not removed during short circuiting. Only sparking it is removed. Okay, so we quantified that, and so this is the this shows. So I will stop this video for a moment. See, so in here, this is a textured surface. This is textured surface, and on textured surface we have put the drop of the water. Okay, so if this is not the hydrophobic surface, this drop will spread immediately. Okay, this drop will spread immediately. Since it is a hydrophobic, this is a textured surface, the drop is resting, and there is this contact angle is there, which gives us the indication of super hydrophobicity. In lotus leaf, you can see this lotus leaf, this is a same image of lotus leaf, actual lotus leaf. On lotus leaf, there are these micro rods are there, around close to the 10 micron size. Here we have made around 40 micron size, correct, around 40 micron size. So this is around 40 micron size, and then we quantified that, and we could achieve this this is around 120 degree. On lotus leaf it is 150, more than 150. So on textured surfaces we could achieve 120, and untextured surfaces, nascent surfaces, it is very close to the 60 degree only. So due to this texture, the hydrophobicity has tremendously increased, although it is not super hydrophobic, but yes, it is a hydrophobic in nature. But actual lotus leaf, there is a micro rods. On these micro rods, there are the multiple rods of smaller dimension. These are called as hierarchical structures. It means rods on the rods. So we also may try to made it. So wherein we have made the rods, bottom rods of 20 micron, 200 micron. So these rods are of 200 micron, and on this 200 microns there are the 400 microns. So these are called as hierarchical structures. So we could make the hierarchical structures, but it is found that even hierarchical structures, contact angle is not changing. So, and it was also out of scope our that, but we have developed the manufacturing process which can make the surface hydrophobic in nature by manufacturing these thousands of rods. And as of now, there is no process other than reverse EDM which we have developed, which can manufacture this sort of textured surfaces, which is called as a positive texture surface. Dimples you can make with the laser, but not the positive textures. Dimpled are known as the negative surfaces. Here we have made the positive surfaces. Okay, but again, question is like, why the process is improving with the ultrasonic? So to prove that ultrasonic is improving, what I have did, so I have done the simulations also for that, to prove that ultrasonic improves the process, improves the debris evacuation. What are the debris? Debris are the particles which are ejected from during the process. So I have assumed that we are manufacturing only single rod. So somewhere here I have taken the problem, axisymmetric problem. There is a dielectric in, dielectric out, and in ultrasonic vibration, this plate is vibrating. So assume that there is some spark took place somewhere here. So whatever is a dotted red line, that is only my area of interest. So that is this zone. It is represented here. So I assume that somewhere here the spark has happened. So in zone 2, somewhere spark has happened. So once there is a spark, in actual case, there are thousands of spark is happening in the single second. But what I have assumed that only single spark is happening. But at that time, nobody were knowing that how many particles would be generated in this single spark. So I have developed the mathematical model for that. uh, Actually caught those debris particles under the microscope, measured that, developed this mathematical model based on the energy equation, like what is the energy of the single spark and how much energy is required to generate single particle. Based on that, balancing that, I have made that, and it is found that those majority of the around 36,000 particles, debris particles, would be generated in the single spark. Okay, 36,000 debris particles of uh, around 90 nanometer dimensions, around 90 nanometer dimensions, thousands of 36,000 of particles would be generated. Now, based on that, I have developed the geometry and try to benchmark this, and then I have done this simulation where I have injected 36,000 of the particles. Dielectric is flowing in this direction and it is ejecting in this direction. And remember, this geometry is vibrating at 36,000 times. You can see the gap between these boundaries is reducing continuously, so it is vibrating. So what, nobody earlier quantified what is the effect of these boundary vibrations on the particle motions. So in the channel, and this is in the millisecond, huh? You can see here the time. During milliseconds, all those 36,000 particles are distributed in the channel, and due to this ultrasonic vibrations, the lot of velocity is given to these debris particles, which is not there if ultrasonics are not provided. And due to this ultrasonic vibrations only, the particles get accelerated and they get ejected from the bottom of this channel, bottom of this pipe. So this ultrasonic, we prove that ultrasonic, with the ultrasonic, the particles moves forward, backward, forward, backward, but there is a net forward movement. And due to this, the particles immediately get escaped from the entry electrode gap, and due to this, the short circuiting is avoided with the ultrasonically assisted reverse EDM. And based on that only, you can machine the hydrophobic surface, without which it is impossible to machine. Okay, so we quantified this, and we quantified what is the effect of frequency at 1 kilohertz, 3 kilohertz, 6 kilohertz. We done all the simulations, effect of frequency, effect of amplitude also. And we said that without vibrations, with vibrations, the particles get velocities double the velocity which is not there. Without no vibrations, particle is around 0.45 is the velocity. With vibrations, it is more than 2.5, almost 5-6 times the particles get the velocity, and they don't get the time to stick there and cause the short circuiting. That we prove there. And that paper was accepted. JMMs is one of the good example, good papers in the micro manufacturing domain, could publish these results in the JMMs paper. Okay, so this is how we could be able to manufacture the hydrophobic surface, bio-inspired surface, in the laboratories. And as of now, there is no manufacturing process which can create the textured surfaces on the metallic surfaces. Okay, so but what is the future of micro manufacturing? Future of micro manufacturing, if you see the video also, we are manufacturing micro parts with the huge machines, so which is a normal size machine. So but the question is, why you are creating such a small parts, and why to use the very large or big machines? Can we reduce the size of the machines as well? So that concept is evolving. There are practical examples also in the micro factories where people have reduced the machine size also. Okay, and good thing is that factory size itself is now close to our table size. So on the table, you can see that there is a milling machine, there is a micro ADM machine somewhere here, there is a punching machine, there is an assembly machine. All are integrated, all are automated. There is a 6 degree six robot of 6 degree of movements, and all movements are possible with these robots, rotational and translational, and it can assemble the parts. So everything is integrated in the small table, and you can do the machining or commercial production of micro assemblies on the small areas. Machines need not to be very small, and now the size itself is close to the micro factory size. Here is another example developed by the microfactory developed by the MITI Japan, where the size of the industry is close to the size of the briefcase. And in this briefcase, there is a micro lathe machine, micro milling machine, micro press machine of these dimensions. Micro lathe is only how much? 3 centimeter by 2 centimeter by 3 centimeter. A small lathe machine, where a small lathe machine, you cannot see the lathe machine. Somewhere here is the lathe machine, which is a production lathe machine. You can do the actual production on that machine. So lathe machine, milling machine, micro press, assembly, everything is done, and you can do the productions within the very small limited area. And these micro factories are evolving. Future of micro manufacturing is very bright. The horse machined or not machined, it is fabricated on the by the MSL process on the photopolymers. These are also polymer made by the polymers. These are also the polymer. This is a metallic. This is metallic. These are also polymers. Okay. Feature of micro machining is this is the eye of the needle, and somewhere here the feature is created, and this, if you zoom on the feature is like this. Okay, so this is the future of micro manufacturing, micro machining, where you can create such a beautiful features. Okay, and in near future you will see that the size of the part itself is a tolerance on the part. As of now, you can, if you create a meter, a rod of a shaft of meter, a meter diameter, the if you have machined in the industry a shaft of a meter diameter, in that case the tolerance on itself is a few hundred microns, but here size of the part itself is in the few microns. So in that case you can thought of the how much tolerance you will provide on that. Okay, so as of now that some of the processes tolerance has become equivalent to the basic size. Okay, so in that case sometimes the part is made and sometimes part is not made at all. So like that the present status of micro machining is there. But yes, you can create lot of features with this, and lot of promising things are coming in the micro machining. So future is there, where your size of the factory would be your palm top. Okay, so thank you. Whatever I wish to communicate, I have communicated and discussed with you. So if you have any queries, questions, you can raise, or you need some discussions on that, you can also uh, note it here, message here.
Yes, thank you, Dr. Sachin. Thank you very much for a wonderful session. You showcase like really the future of manufacturing through your this particular talk, and really the bio-inspired designs and how we can mimic it through the micro machining.
Correct.
Many more case studies you have shared, particularly the lotus effect and all, how it can be achieved. And yes, there are many things we can get inspired from observing the nature and we can mimic. I open this forum for the participants to discuss with the Dr. Sachin. Participants can unmute themselves and discuss. Any questions?
Anybody has worked in the micro EDM domain? Okay, nobody has worked. Good.
There are few compliments uh, for you, Dr. Sachin, and I think Chetna has raised the hand. Yeah, Chetna,
Yes, Chetna, yes.
Sir, I have one question. I just wanted to know, like, what all are drawbacks basically with the micro devices? With so you were mentioning some high aspect ratios, no?
Correct.
So so how do you like whenever we improve some high aspect ratios, what all drawbacks or what all challenges you have faced? Uh,
So
Basically for
challenge
TV devices, huh?
challenge is always like if you try to make it smaller,
Hmm.
the inherent strength of the features loses. Correct. So for example, there is a one shaft of 1 mm and shaft of 10 mm. Although shaft of 10 mm is 10 times larger in diameter, but it is 1,000 times more strength. So like that, if you try to reduce the size of the features, its strength diminishes at accelerated rate, at a higher rate. So that is creating the problems. Although we can create, let us say, that micro shaft, but you cannot use the micro shaft in the micro motors because the shaft has already lost its strength and it cannot drive the accessories which are attached to the motors.
Yes, sir.
So these are some of the things. Also, during machining, always there is a residual stresses are there, due to which the thin features become bent and lost their initial or intended geometries. So these are some of the drawbacks of micro parts. But
And what about sir scaling?
scaling means what?
The scaling laws. So whenever we reduce the size at that particular time along with shaft, so it won't carry the entire assembly. But again, how do we manage that scaling? Basically, reducing the entire size.
That is always challenging. But
Hmm.
whenever you can use this type of features, whenever there is a no, they are not in contact with, physically not in contact with the other systems, like a sensor, for example.
Hmm.
In
Correct.
that case, the strain doesn't matter that much. In that case, you can use these features.
Yes. Yes. Thank you, sir.
Thank you, Chetna.
Uh, any other questions from the
Any other
participants?
questions? Okay, don't think there is a questions.
Yeah, sir, there is a question from Professor Hashin, sir.
Yeah, Professor Ashin, good.
So, yeah, Professor Hashin,
Yes, sir. So, sir, I want to know for making the textured surfaces.
Ha,
So many times the non-conventional machining is preferable.
correct.
Okay, but is there any conventional way of machining
Okay.
to make it possible?
Conventional way is, let us say that you want to create some texture on, let us say, simplest way of observing the texture is during our travel in the locals, for example.
Correct.
The rod at the entry gate is there is some texture is there on that.
Yes.
Similarly, that texture is produced by obviously the other tools, but rolling, with the rolling, you can create the texture on the surface. For example, you are carrying out hot rolling process, for example.
Yeah.
So on the surface of the roll, you already put the negative texture. Whatever you wish to be texture on the surface, put the negative texture on the rollers. So once you roll the surface, that roller, whatever is the texture on the roller, is impregnated on the surface.
Correct.
So there is a rolling is one example. Laser, you call laser as conventional or unconventional machining process, but laser is very widely used to produce the texture. And as of
Yeah.
now, all commercial texture is being produced with the help of lasers only.
Yes, sir. Yes, sir.
And
Yes.
if it is not the deterministic, for example, abrasive jet machine,
Yeah.
you take a abrasive jet machine and put the abrasives on the surface, like a sandblasting process. It will
Correct.
create the texture, but that is not the deterministic. The way I have created the texture on the surface with reverse idiom is deterministic. Correct. You can
Yes.
play with the size of the micro rods, their spacings, their diameter,
Controllable dimensions.
controllable dimensions.
Correct.
But with the abrasive jet machines, it would not be a controllable. It is a probabilistic. Everything is probabilistic, not the
Correct.
deterministic.
Yes, sir. Yes, sir. Thank you, sir. Thank you, sir.
Yes,
Thank
yes,
you.
Hello.
yes, yes, sir.
Uh, Good evening, sir. I'm Dr. Prashant. Sir,
Yes,
I have a question. Sir,
yes,
these micro tools are extremely small in
yes,
diameter.
Yes.
So what about tool wear and breakage of the tools, sir?
Earlier days, see, the micro machining process were evolving. So as I mentioned, that half of the tools will break before we actually receive the shipment in the IITs.
Okay.
So, but later part, it is found that their manufacturing process, tool manufacturing process, has also become more stabilized. And later part, we found that even Indian made tools are giving the good results. After 5 6 years of down the time, we found that they are equally comparable, or they are have good quality compared to the Singapore tools also. But yes, uh, that is the most, uh, difficult, or it is always a challenging to control the failure of the tools. And all these mechanical tool fail without giving any warnings, specifically in the micro tools. Okay, so sometimes tool will last for completion of few components. Sometimes you require 10 tools to component, 10 tools to machine a single component. So it is totally depends on the how tool behaves, number of factors. Is there any vibrations, whether you have properly mounted the tool on the spindles, all those things. So but it's
Okay.
if it is at the micro level, it's very difficult, very difficult.
Okay, sir. Thank you.
Yes, yes. Okay.
Yeah, thank you, Dr. Sachin, for very informative session. You take up this manufacturing at the end to the next level by showing something very different, which we can see from observe from the nature, and really implement in the design strategies and mimic it and for various applications. And the solution perhaps may be a sustainable, that also you can address. So
Yes.
thank you very much for this session,
Thank,
and from the Sardar Patel College of Engineering, and also on behalf of all the participants, and also from the AICT, I thank you for sparing this time and giving the insights. Thank you
thank,
very much.
thank you. Thanks for giving me opportunity to interact with the huge crowd. Okay.
Yeah.
Thank you,
Okay.
organizers.
Yeah.
Okay. Thank you.
So participants will proceed for the validatory function straight away. Over to you, Professor Deepak.
Yeah, thank you, sir. So it was a wonderful session by Dr. Sachin Mastood. We are very grateful for his session. Thank you, sir. So whoever the participants have joined now, good evening, everyone. Now, as we move on to our validatory session, it gives me immense pleasure to welcome you all to this validatory session for our 1 week faculty development program on shaping the future of manufacturing with 3D printing techniques. Through this week, we witness remarkable participation, insightful discussions, and valuable knowledge sharing. The technical depth brought in by our distinguished speakers has truly enriched this FDP and strengthened our understanding of advanced and emerging manufacturing technologies. We are very grateful to all of our experts from academia, research labs, and industries who have accepted our invitation and contributed their expertise. Your sessions have added tremendous value to this program. Now, as we move on into the concluding part of today's event, we will now hear closing reflections from our FDP organizing team. Now, as we proceed with the closing reflection, I would like to begin by inviting our co-coordinator, Dr. Basme sir. So, Dr. Basme is an assistant professor in the Department of Mechanical Engineering at SPCE. He brings over 20 years of academic and research experience to the institute. His expertise spans in aerodynamics, energy system modeling, heat exchanger design, and solar thermal systems. He completed his PhD from IIT Bombay, contributing significantly in the thermal sciences. He is actively involved in teaching, research, and departmental development as SPC. Through his dedication, Dr. Basme has played a key role in the smooth coordination of this FDP. Now I request Dr. Basme to please address the participant. Over to you, sir.
Thank you, Deepak, for such a nice introduction. Am I audible?
Yes, sir.
Yeah, yes, sir, you're
Yes,
audible.
sir, you are audible.
Yeah. Good evening, everyone. Uh, the head of the department, Dr. Santosh Rane, sir. Uh, then Sardar Patel College of Engineering, Dr. Kiran Bhore, course coordinator of this FDP. Associate Professor and Dean R&D at Mechanical Engineering Department, Sardar Patel College of Engineering. Then other faculty members of the department and other departments, participants from all over India, from various streams of engineering and maybe research. As we come to the conclusion of this enriching 6-day ATAL faculty development program on shaping the future of manufacturing with 3D printing techniques, it gives me immense pleasure to say a few words in the valedictory function as a co-coordinator of this program. Over the past 6 days, we successfully conducted 13 insightful sessions delivered by distinguished speakers from India and abroad. We have 4 to 5 sessions from abroad conducted by, they have joined early in the morning also. One is from second session, Dr. Datta Parle has given a session on expanded horizons of materials for 3D printing. Then Dr. Zeba also joined the second day. Then we had, Dr. Kedarnath Rane, and these are from outside. Then outside of India, Ajinkya Shetty. Then we had Vinaya Manvatkar today, and other distinguished speakers like in the inaugural session, Dr. Guru Prasad Rao and other distinguished speakers from India. So we are deeply grateful to all these esteemed resource persons for sharing their expertise, experiences, and time with us. Your contribution have truly elevated the quality of this FDP, sir. A special appreciation goes to all our participants who joined wholeheartedly every evening after their college hours or office hours. So your dedication, involvement, and active participation were truly commendable. Your enthusiasm kept the program vibrant and meaningful throughout. My sincere thanks to our principal, Dr. M. Muridi, HOD of the Mechanical Department, faculty colleagues for their constant support, coordination, and encouragement in organizing this FDP smoothly in the online mode. Last but not the least, I extend my gratitude to entire organizing team, technical support members, and everyone who contributed directly or indirectly to the success of this program. Thank you all once again for making this FDP a memorable and productive experience. Wishing you a very best in applying these insights to your teaching, research, and professional endeavors. Have a wonderful evening ahead. Over to you, Professor Deepa. Thank you.
Thank you, sir. Thank you for your kind words to everyone, sir. Thank you so much. So now we move on to our faculty development program coordinator, a person who has planned this under his leadership and constant involvement. I'm pleased to invite Dr. Bhole. Dr. Bhole is an associate professor in the mechanical engineering department at SPCE. He has over 25 plus years of experience in academic and research. He serves as a dean R&D and dean PG program. He significantly contributed to the overall development of a research ecosystem at SPC. He has guided 5 PhD scholars and more than 20 MTech students. His research interests include microfabrication, microfluidics, and additive manufacturing. With his leadership and planning, Dr. Bole has been instrumental in the successful execution of this FDP. Now I welcome Dr. Bole, sir, to please address the participant. Over to you, sir.
Yeah, I'm audible to all of you.
Yeah, sir, you are audible, sir.
Okay, so thank you, Professor Deepak, for introducing me as a coordinator to all the participants. I take this opportunity in the valedictory function to thank very first to the AICTE ATAL program, because this is the driving source. AICTE has started this ATAL initiative, and that's why we are able to gather and discuss over this particular week the various on various topics on the 3D printing and shaping the manufacturing, shaping the future of manufacturing. So thank you for this wonderful initiative of the AICTE, which has made this particular event possible. Also, I thank my institute, Sardar Patel College of Engineering, the leadership of the Sardar Patel College of Engineering, the head of the institute, Dr. M.M. Murdi, the head of the department, the then head of the department, Dr. R.S. Moria, and the present head of the department, Dr. Santosh Rane, for but the guidance to this particular program and giving us opportunity to present this proposal and making this event a successful. I also thank my co-coordinator, Dr. Basme, who supported me a lot in this particular week. I was busy in many other important assignments which has come, and sir has shouldered the responsibility quite well, and uh, has executed all the session and was with me all the time. I also thank my other team members who are there present, who actually monitored and also the moderated the most of the sessions. So I thank the Professor Deepak, Professor Sharad Vadavi, Professor Hasid Sheikh, and all other those who took the participation in making this event and this FDP successful. Behind this program, there are many other hands, such as non-technical people, with me who make this proposal ready, and also all sort of like the procedural activities, such as Mr. who which are very very important. So I thank all them, like Mr. Lewis, then all other team members online, and the system operators who are behind this particular show. So thank you to all those who are directly, indirectly involved in this particular program. I also thank the speakers of this particular program, as already being mentioned by Dr. Basme, who delivered their lectures in this program and make this program more informative, and technically enriched. I also thank the participants. Really, the Dr. Busman made it clear that the participants made this program vibrant. This program designed in the evening, as it is an online, and as per the AICT mandate, we started it at the 6 p.m. Somebody is on, I think. Some noise is coming. Deepak, can you moderate it? Yeah.
Yes, sir.
So,
Yeah.
so this program, as per the AICT mandate, started in the evening at 6, and we know, and most of the faculty member, after completing the duties, it's a tiring and going and reaching the residence and starting this learning activity is really a challenge. And but the participants were really wonderful. Their commitment, their involvement. I know, like in many of the sessions, like Professor Subbu, Professor Sarvana Kumar, who is from IIT Madras and IIT Palakkad, they had interactive session right from the minute one, and participants were on the toes and discussing and the discussion took place almost on the every questions they asked. And today also, like the Abhishek discussed a lot, and participants responded well. So it gives an immense pleasure and happiness, when the participants are there with this particular program and with the speakers. So thank you for such a wonderful participation. And as an initiative, I started in this particular program that in online we do not meet face to face, and I started initiative to make the participant to introduce the speaker, and many of the participants responded to that particular call. I could not give the opportunity to all the participants because of the constraint, but really those who participated, thank to them, and those who listen also thank to them. So overall, it was wonderful journey this 6 days. And the last, just as a coordinator role, I just wanted to tell all that there will be a test exam. Do not panic. Give the best in the test exam. It is more on the fundamentals and concepts, as the your diverse background is considered while making this test exam. So do not panic. It's based on more on fundamentals. Really, you will not be tested more rigorously there, but your fundamentals will be tested there. So do not panic and give it with the preparation. The test will start at 8 p.m. and it will be there for 24 hours valid, but I will appreciate if you finish early by today, or at the most by tomorrow 11 or 12 p.m. Okay, so that will avoid any consequences and any issues if in case of some the test exam appearing to the test exam on time frame and all. So hope this particular note you have noted it, and be on timeline while giving on the test exam, and have ensure that there is a network, a stable network when you are giving the examination. Again, I thank all of you from my coordinator side and from Institute AICT side. Over to you, Professor Deepak.
Okay. Thank you so much, sir, for your kind words. As a participant, I feel the FDP was really fantastic. All the experts who were legend in their field, they have given their and shared their knowledge, so it can be passed through different generations, and we are all very happy now. As we know that we all have someone who is the torch bearer, who shows us the right path, and who guides us in every situation. For us, it was our head of the department. So it is my honor and privilege to invite our chief guest and the head of the mechanical engineering department, Dr. Santosh Rane, sir, to deliver his valedictory address. Dr. Rane's vision, leadership, and continuous support have been central to the success of this FDP. His presence today as a chief guest adds a great value to this concluding session. Dr. Santosh Rane is a head of the mechanical engineering department at SPC with over 33 years of experience in engineering, research, consultancy, and academic leadership. He holds a MTech and a PhD from VJTI Mumbai. He is a master black belt in Lean Six Sigma. He is also a certified reliability engineering professional and a trained in advanced project management from SPJMR. His research interests include reliability engineering, Lean Six Sigma, industrial engineering, project management, and production management. Dr. Rane has mentored 450 plus business excellence projects for multinational industries. He has authored 120 plus research publication and holds 12 granted patents out of 27 which are filed, and has received more than 3,290 plus citation on his publications. Dr. Rane has guided 14 PhD scholars and 30 MTech students, contributing significantly to the advanced research. He has held major leadership roles, including chairman IIIE Mumbai chapter and vice chairman SAE India Western section. His guidance, vision, and support have been pivotal in shaping and strengthening this FDP. I now request our chief guest, Dr. Santosh Rane sir, to deliver his valedictory address. Over to you, sir.
Thank you, Professor Deepak. Thanks for your kind words. There is a little correction in the PhD guidance and the mentoring. Total number of students guided and mentored are 14, out of which 8 are guided and 6 are mentored. Thanks for the same. So good evening to everyone. It gives me immense pleasure to have a word with you all at this valedictory session of our 1-week faculty development program on shaping the future of manufacturing with 3D printing techniques. Over the past 1 week, we have witnessed remarkable participation from you all, insightful discussions, and enriching interactions that truly reflect the spirit of continuous learning and the academic growth. At the outset, I wish to express my sincere appreciation to all our distinguished speakers who join us from the premier institutions, research organizations, and the esteemed industries across the globe. Your contributions, expertise, and willingness to share knowledge have added tremendous value to this faculty development program. Each session has broadened understanding of advanced manufacturing, additive technologies, and the rapidly evolving industrial landscape. I would like to acknowledge and congratulate our FDP coordinator, Dr. Kiran Bhode, and co-coordinator Dr. Balwant Bhasme for their dedicated efforts, excellent planning, and seamless execution of the program. As per my understanding, Dr. Kiran Bhole has brought 7 to 8 such kind of ATAL FDP to SPC and also motivated other faculty members to do the same. Coordinator and co-coordinator and their commitment behind the scene ensured that every session proceeded smoothly and meaningfully. A special word of appreciation goes to all participants. Your enthusiasm, active involvement, insightful questions, and consistent engagement made this entire program vibrant and impactful. I'm confident that the knowledge gained here will encourage you to innovate in your institutions, strengthen your research pursuits, and inspire your students to explore emerging technologies. I also thank our Honorable Principal Dr. M. Murdi sir, Management of SPC Dr. Shesha Iyer sir, administrative staff and technical team for their consistent support throughout the organization of this FDP. As we conclude this 1 week journey, I strongly believe that learning of this program should act as a catalyst for future collaborations, interdisciplinary research, and academic excellence. 3D printing and digital manufacturing are transforming industries at an unprecedented pace, and as educators, it is our responsibility to stay ahead, adapt, and contribute meaningfully to this evolution. Let us continue this momentum, explore new possibilities, work together towards strengthening the academic and research ecosystem of SPC. We have excellent infrastructure for the same, and I would like to invite the participants to join us for taking the research ahead. Thank you all once again for your participation, support, and commitment. I wish you great success in your future endeavors. Have a wonderful evening. Thank you.
Thank you, HOD sir. It was very much nice of you for having such a sweet words for everyone. And we are very much thankful that from your busy schedule that you took your valuable time and guided us through all this. We are very much grateful to that. Thank you, sir. So before we close, it is important for us to hear from our participants. Your experience, feedback, and reflection will help us to understand the impact of this FDP and guide us in future programs. And now I invite a few participants to share their thoughts about their learning experience during the our FDP program. Participants, please, you may raise your hand. Whoever is interested to speak, please raise your hands, guys.
I request Dr. Mahesh Bhivapurkar to kindly say a few words. Dr. Mahesh.
Yeah, sir. We'll go one by one. Many of the participants are interested.
That's great. That's great.
Yeah, sir. So, Dr. Sachin Kamble, please share your views, sir.
Yes, sir. Yes, sir. Thank you, sir. Thank you for this opportunity, sir. Am I audible, sir?
Yeah, you are completely audible, sir. Please.
Okay. Good evening, all respected organizing committee members and participants. The ATAL FDP on shaping the future of manufacturing with 3D printing techniques, which was organized by Sardar Patel College of Engineering, Andheri, since 1st December. Now about this FDP, the title and topics chosen for this FDP are most relevant and important for the future manufacturing processes. No doubt, the resource persons chosen for this FDP are clever, knowledgeable, and good.
Sachin sir, you are muted. Please, sir, unmute, sir. Sachin sir.
Good evening, sir. Good evening. About this FDP, the title and topics chosen for this FDP are most relevant and important for future manufacturing processes. The resource persons chosen for this FDP are clever, knowledgeable, and good presenters. The depth of topics delivered by these resource persons was well enough and has imparted very useful insights. About the time, the punctuality and overall organization was well, and it was appreciable. So special thanks to the principal of SPCE, then course coordinator Dr. Kiran Bole sir, co-coordinator Dr. Basme sir, you Deepak sir, then Dr. Rane sir, who has just talked before my feedback. Thanks to all the resource persons for their valuable contributions, and overall it was an excellent experience to be participated in this FDP. Thank you for this type of FDP. In future, also such FDPs should be organized so that we can get more and more knowledge. Thank you once again to everyone and all the participants. Thank you.
Thank you, Sachin sir, for your kind words. Thank you so much. Now, I request.
Sir, I would like to say something.
Yeah.
Sir.
One by one will go, sir. No, one by one will go, sir. Now I invite Dr. Srinivasa sir to please share his views, sir. Srinivasa sir, please, over to you, sir.
Yeah, good evening, everyone. Good evening, Deepak sir, and good evening, Kiran Bole. Actually, I have attended all the sessions and observed that the content that is being given is wonderful. And I request the organizers to please share the PPTs as much as possible if the resource persons have given them. And most of the resource persons are giving the extraordinary content and advanced content of the 3D printing, and some of them are excellent or beyond excellent. And I want to thank all the participants, because most of them, when I see, everyone almost 140 to 150 are there till 9 o'clock, and I appreciate all of them. And also, I would like to appreciate the organizers mainly, because not only us, even you also, because we just say login and we will be listening. If we lose the internet connection, okay, we will rejoin. But from your side, it is seamless, and all your team members are, maybe they are also, especially they are also after working the full day and they need to go back to home, and they are doing again duty and making it a seamless connection and without any disturbance. I haven't seen any disturbance in all the sessions, all the 13 sessions. Such a wonderful FDP organized by SPCE and the team. And congratulations and thank you. And thank you once again to everyone. Thank you, sir.
Thank you so much, sir, for your kind words. Now I request Mahesh Bivapurkar sir, please, sir, share your views, sir.
Uh, Thank you, sir, Dr. Bole. Thank you, Rane, sir. Initially I started my career from the SPCE Mumbai. Now I am a dean of OP Jindal University, Raigad, in mechanical department. This FDP really benefited me for the advanced knowledge whatever we have in conventional system. So how we can utilize this AI and ML technology in our additive manufacturing. At the same time, the last session was really very wonderful. What is the future scope of EDM process will be there. So not only to the researcher, not only to the new faculty member, to me also as a senior most person. So this emerging technologies in the mechanical department, I really benefited from this. So thank you, Dr. Bhasme. Thank you, Dr. Kiran Bhole. Thank you, Rane sir, for say organizing such a wonderful session and well coordination among the well coordination by the faculty member of the SPC. Thank you, sir.
Thank you so much, sir, for your guidance and your blessings, sir. And we are very grateful that you were part of it, sir. Thank you so much, sir. We are very much grateful to have you, sir. Thank you so much, sir.
Thank
so
you.
now I request Mr. Deepak Kharat to please share his views, sir. Please, sir. Yeah, Deepak Kharat sir. Yeah, you wanted to share some.
Yes, yes.
Please, sir. Please, sir.
Good evening, sir.
Yeah. Good evening, sir.
Myself, Professor D.P. Karat from Padma Shri Dr. V.B. Kolte College of Engineering, Malkapur. Sir, the session is conducted by the expert is very wonderful. Whatever the knowledge I get, I am very interested to do my research work in additive manufacturing. So whatever my concept is there, that will definitely this FDP will helpful for me to further go my research work. Thank you, sir, our team and our college, your college. Thanks, and thanks to ATAL FDP also. Thank you, sir.
Okay. Thank you so much, sir, for your sharing your views, sir. Now I invite Chetna Sharma, ma'am. Please share your views, ma'am.
Thank you, Deepak sir. So I would like to introduce myself. So I'm Chetna. So basically, I worked in SPC as an ad hoc. Then I've completed my PhD under Bhole sir only, and this is my third FTP with 3D printing from SPC only. So I really enjoyed all the FDP sessions. The concepts were very relatable, and since this was the third one, so I really like the nature inspired surface textures, and the Abhishek sir's session where he have clearly mentioned the role of AI and LLMs in additive manufacturing. So all the experts talk on 3D printing, embedded sensors, and all sort of advanced AM processes were very strong, very future ready FDP. The content was very future ready, and it was very meaningful to us. So we were spending majorly after our working hours only. So major time was spent after our working hours only. So it was very interesting. So keep it by keeping us involved, and it was very meaningful to us. So thank you very much, all of you, all the organizers and everyone.
Okay. Thank you, ma'am. Thank you for your words. Now I invite Dr. Prathamesh Poddar to please share his views, sir. Sir, please.
Hello. I hope I'm audible.
Yeah, sir. You're audible. Please continue, sir.
Yeah, thank you. Good evening to all. First of all, I'd like to express my sincere gratitude to my research guide and mentor, Dr. Rane sir, and head of the department, Mechanical Engineering, Sardar Patel College of Engineering, for his continuous support and motivation. Then I would like to extend my heartfelt thanks to Dr. Kiran Bole sir for giving me the opportunity to attend this FDP, shaping the future of manufacturing with 3D printing techniques. Thank you, sir. Although my background is not from 3D printing, the FDB has significantly enhanced my understanding of additive manufacturing technologies. The sessions were very insightful, well structured, easy to understand, and even for participants from different engineering fields. Attending this FDP has also opened a new research domain for me, particularly in exploring how 3D printing can be applied in automotive sector, uh, particularly in design, lightweight structures, sustainable materials, and rapid prototyping. This exposure has broadened my research vision and inspired me to explore interdisciplinary applications of advanced manufacturing. I sincerely thank the organizers and all other resource persons for conducting such a valuable and enriching FDP. Thank you once again for this wonderful learning experience. Thank you.
Okay. Thank you, Prathamesh, sir. Is there any other participant who is willing to express his view or share his experience? You may please do.
Sir, I just want to tell one more point. I am from Hyderabad. I
Yeah,
have
please, sir.
nothing with the SPC because when I saw some of the participants, most of them are nearby our SPC. I am from Hyderabad, Anurag University. I am the associate dean and also the HOD Mechanical Engineering, Srinivas Chalapati. And yes, as I said, all the sessions were wonderful. Thank you.
Thank you,
Thank you,
sir.
sir. Thank you. And we are open for the collaboration. We'll discuss separately on those issues also, Srinivasa sir. And we'll happily do like the common areas and domains where we can collaboratively work. Thank you, sir. Thank you. Thank you being part of this FDP, and I was observing you. You are very one of the very sincere participant in this FDP. Thank you, sir.
May I, sir?
Yeah, you may, please.
Yeah, please.
Yeah, good evening, everyone. This is Nehal Muchala, and I have
Yeah.
done masters from SP College of Engineering, and I'm doing right now pursuing PhD from VJTI, and I enjoyed really all the sessions. I attended previously also few FDPs organized by Dr. Kiran Bole sir. So we are honored to attend this additive manufacturing FDP, and it has enriched really knowledge of our all type of researchers. Thank you very much, sir, for giving such insightful sessions. Thank you very much.
Yes, thank you, ma'am. Thank you.
Any other participant who is interested in sharing his opinion and views, please, you are welcome. Anyone?
So, Mayor sir, good evening.
Yeah, good evening, sir. Please, sir. Yes, you, please, sir.
Sir, just wanted to express the thanks to all the organizing team. Just wanted to mention one thing that I'm not belonging to the mechanical background. I'm just from the chemical engineering background. But still, because see, just nowadays for the NAP and all the thing, we have been going for the multidisciplinary all the thing. So having some little bit of interest in the subject, that's why I've been chosen this particular FDP. And it was really a wonderful experience. The speaker and the way you had been handled the FDP was a wonderful sessions. So thank you all the organization and the team. Thank you so much.
Thank you so
Thank
much,
you
sir.
very much, sir.
Thank you, sir. Thank you so much. Thank you, Bode sir, for giving the opportunity for attending this FDP.
Yes, thank you. Most welcome, sir.
Thank you, sir.
Okay, is there anyone else who wanted to share his views or share his experience? We are very much eager to listen to them. If there is anyone who wanted to share his experience, is there anyone? Participants, do you wanted to share your experience or your opinions? We are welcome to listen to you.
Good evening, sir.
Yeah, good evening, sir. Please.
Yeah, I'm Dr. Prashant. So I have attended this FDP, and it was all the sessions were so informative. So I was not knowing much more about additive manufacturing, but after attending this FDP, I have learned many things about additive manufacturing. So thank you, the organizing team, for organizing such a wonderful FDP. So in future also, if such FDPs are organized, so I will surely attend such type of FDP. Thank you very much.
Yeah, thank you so much, sir, for
Yes, thank
being
you.
present in all the sessions, sir. We are very much grateful that a good FDP is when the participants are always active and enthusiastic about learning new things. So all the participants had made this FDP a wonderful. So if there is anyone else who wanted to share his views or share his opinions, we are there. So please, we are waiting if you wanted to share, sir.
Hello everyone.
Yeah, sir, please continue.
My name is Jitendra Thombre. I am from New Horizon Institute of Technology and Management. So the glory of this program, what I observed is that in addition to the academicians, the people from the industry which you added and the the type of the delivery or the quality of the work what they have done and which has really forwarded us as far as the knowledge is concerned and the new technology we could at least get some access which can explore that has been added to our knowledge. So I really want to thank to Dr. Kiran sir, Dr. Basme sir, and all Santosh sir that you really have made some taken some effort to really invite the people like this who has really contributed to our knowledge and forwarded us as far as the additive manufacturing technology. Thank you so much.
Thank you, sir, for your kind words, sir. We are very grateful that you were part of this FDP, sir. Is there any